Hello everyone, welcome back to my YouTube channel. If you're watching this, it is because I am at the zoo watching all the animals. I hope to see Kia the harpy eagle because she's my favorite, and then I want to see the sloth and the naked mole rats in the underzone. Also, I would like to see the tortoises. They all have names. I think my favorite is, I think his name's Seven. Oh, and then the painted dogs. I just like all the animals at the zoo. But I still have to teach you thermodynamics, so here we are. So Unit 8 is thermodynamics. You can take an entire college class over this, but we're going to do it in 3 weeks. And I've taken that college class, and it's fine. Okay, so in the past, throughout this year, we've been looking at like big objects, so like animals and planets, and like I don't know, bowling balls. But for Unit 8, we're going to zoom in on smaller objects, like individual like particles of gas, but not too far that we get into quantum physics, just like small enough so that we can also call it chemistry, because it's literally the same thing that you did last year in chemistry. It's just in this physics class, because Dr. Moyer loves thermodynamics. Okay, so the thermodynamics equations for this homework are going to be like right here. And I'll just like break it down. I'll just like pull the equation aside as soon as we need it, so not to like give you all too much all at once. I'm pretty sure like AI does that anyways. So we'll just start with like, this homework is kind of nice because it kind of goes in order. So like you just start from here, start with that equation, then you'll end with not these equations, but like these equations. So it's kind of convenient in that sense. So we'll just go right away to number 1. And number 1 looks like this. I'm pretty sure everyone has the same number 1. But it's asking you when Celsius and Fahrenheit are the same temperature. So you have the equations, like the very first line is how to convert between different units of temperature. So we've used, in America, we use Fahrenheit most often. I think Fahrenheit is like the superior temperature scale, because like it's like numbers we actually like use. It doesn't like 0 and like 100 in Texas. We don't go wrong on negatives. But for TF is Fahrenheit, TC is Celsius. If it doesn't have a subscript, this means Kelvin. Kelvin. And we use Kelvin when we do math because it can't be negative, so we don't like destroy the laws of the universe if you get a negative answer, because it can't be negative. So if we want temperature in Fahrenheit and Celsius to be the same, right, we have to use one like that has both of them together, so it's probably that one. And if they're the same, then you can make them the same variable. So like whatever variable you want, I'd be like Bryn and use a smiley face. So a smiley face is equal to 9/2 smiley face plus 32. You solve for a smiley face, and that will be your answer. But you have to convert it to Kelvin. So then you use the next equation to convert to Kelvin. So just like add 273 to whatever you get, and that will be your answer you put in the class. So like that's how you do that. The next one is a thermal expansion. So thermal expansion, I'm pretty sure in every class, unless I forgot, I did like the ball in the hoop, where before I heated up the ball would fit in the hoop, and then I put in the hot plate, the ball expanded, and it didn't fit in the hoop. So whenever things get hotter, they expand. Whenever things get cooler, they contract. Contract means to get like smaller. And you have the equation here for thermal expansion, where like L is length, so this is delta, it's change. So change in length is equal to this alpha. This is just like coefficient, it's a constant, and different for each substance, times your original length, right? The little 0 is original, and then times your change in temperature. And that will give you the change in length. So for number 2, we were looking for like the change in height of our thing whenever it expands. So we're looking for like this height right here. And the easiest shape to work with in physics is a right triangle. So I'm gonna do, like, if you can draw a right triangle, it will make things a lot easier. So I can draw a right triangle kind of like this. And then if you know two sides of a right triangle, right, you can do trigonometry to find the other side of the right triangle. So if I know this side, I'll call it A. And I know the hypotenuse, I'll call it B. I can solve for, or I'll call it C. I think I said B, it's C. I can solve for the side we want, which is like B. So A is like halfway in between our like bridge. So if the whole thing for me is 400, that means like half of it is 200. Right? Again, mine's 400, you have a different number. So no A, easy. C is how much this thing like expanded, which we can use the equation to figure out how much it expanded. And then if we want the length, right? So for my random example, it's not, I don't think this is actually the answer, but if I find like delta L is 2, that means like C is like the original length plus my change in length, right? So I'll do like plus 2 or whatever number that is. So then you can find C using the equation, right? And then you can do trigonometry to solve for the height, right? And I trust that I can do that because we know everything in this equation, right? The coefficient they give to us, it says thermal coefficient is this. The units are like per Celsius. So when the -1 is just the unit. So whenever you're doing your math, just worry about the number. We know the original length. But you do have to be a little careful on the original length because it's just only one of these things expanding, right? We're just looking at one of them, not like both of them. So the original length is like this length right here, which is halfway. And then they give us the change in temperature. So then you can do it and solve for B. So then the next one's very similar, but instead of it being like change in length, it's change in volume. So it's literally the same equation, but you just replace length with volume. So we'll do, so it's change in length is equal to alpha, original length, change in temperature. Change in volume is equal to, you can call it alpha, but technically it's like a different constant because it's like volume instead of length. So it's beta, but it's the same thing, times original volume times your change in temperature. Okay. So for number 3, it's a sphere of mercury, and it expands, and it goes up into like this cylinder right here. And we have to find the height, right? Find the height of the cylinder. So whenever our mercury expands, right, that change in volume goes to the cylinder. So the change in volume of our sphere is equal to the area, or like 3 areas, so volume of the cylinder. All right, the cylinder is the capillary tube. And the volume of cylinder is like the area of the circle, which is pi r squared, times the height of our cylinder, which is what we're trying to solve for. We're trying to solve for height. So then if you know everything, right, if we know like beta, the coefficient, right, right there. If we know the original volume, which you can solve for, right, because the volume of the sphere is 4/3 pi r cubed. They give us the diameter of the sphere, so you can use the diameter to solve for volume. So we can know the volume of the sphere. And we know the change in temperature, right, they give it to us, minus 14. Yours is something else. That's equal to pi. You know what pi is. It's 3.14, or we can like put in the pi button in the calculator, times the radius of the circle. So the circle is right here, like the capillary tube. Right, that's the diameter, so you can use the diameter solve for radius squared, and then solve for height, right? So then you'll know everything except for h, and you just do algebra to solve for height. Okay, so those are like the thermal expansion ones. The next math questions are with gases. So we can start with the ideal gas law because it's what you use in chemistry. So it's the exact same thing where P is pressure, V is volume, N is number, or N is moles, little n is moles. So all right, little n is moles. R is that gas constant that you've used in the past, right? R is a constant, it's that number. And T is temperature, right? You just have to make sure temperature is in Kelvin, and it reminds you to do that. Okay, so it's the same thing that you used in chemistry. But since we only have like this R right there, and it's in joules and moles in Kelvin, that means our pressure has to be in pascals or Newton per square meter, right? A pascal is a Newton per square meter. And your volume has to be in cubic meters, right? Just so that our units all match up, because a joule is a Newton meter. So everything has to be in newtons and meters. So that means if they give you liters, you have to convert to cubic meters. And there's the conversion. And if you're given ATM, you have to convert to pascals, and they also give you that conversion. Right? So you always start with PV with nRT, because like that's the one you're most familiar with, and you can like do it. So pressure volume is equal to number of moles times R times temperature. And make sure your temperature is in Kelvin. So like T is in Kelvin. And then you should be able to do number 6. So the other equation is like this one. So the other one is PV equals big N KB times T. So everything's the same. P is still pressure, V is still volume, but except this big N is number of molecules. And so instead of using like moles, it's literally the number of molecules. So like 2, but usually it's bigger than 2. And then KB is, that's another constant. It's called Boltzmann's constant. Boltzmann, I have no idea how to spell it, but whatever. I think that's how you spell it. So it's just your R divided by Avogadro's number, right? And Avogadro's number is right there. So it's just like a different way of doing the ideal gas law. So instead of looking at moles of particles, you look at like how many, like the physical number there are instead of moles, and you'll use Boltzmann constant instead of R, but it's like the same one. So sometimes using this one's easier, sometimes using this one's easier. You just have to choose the one that works best for you. Okay, so number 7 has to do with like kinetic molecular theory, and those equations are underneath your ideal gas laws equation. So this should be a T. So they're all like different ways of saying the same thing. So if temperature goes up, that means like energy goes up, right? Increase in energy. Energy. And with an increase in energy, this also means increase in speed of your gas or your velocity, whatever you want to call it. All right, so you see that here. It's like temperature goes up, then this U represents like internal energy. So it's like all the energies of your gas combined. So it's like all of its kinetic energy, all of its like rotational energy, like everything. We just call it U, and that's internal energy. And it's equal to like 3/2 N, right, little n, number of moles, R, that constant, times T. Make sure T is in Kelvin. So this 3/2, if you really want to know where it comes from, you can take physical chemistry 1, but you just have, for this class, it's not really important where it comes from, but it's 3/2 N RT. Right, that's internal energy, like all the energy of the gas combined. So then the one in the middle, it's like the same thing, but instead of looking at like, or I mean, we'll do like, this is like total internal energy. So you'll use this one if you're looking for like all the energy of all gas molecules combined. So then the middle one, it's like the same thing, right? You see the 3/2, you see the T, and instead of moles and R, it's Boltzmann constant. But this, now you're looking at, so 1/2 mv squared, that looks like kinetic energy, and this bar means average. So this is like average kinetic energy. And you'll use this one mostly if you're looking at like for like a single particle, instead of like the whole thing. And then this one, the first one, is kind of similar, to like this one, but like rearrange. So if you really want to do the math, you'll like see like this one is also equal to like both of them combined. But you'll use this one if you have like pressure, volume, number of gas molecules, whatever. But the three equations just like three different ways of saying that if temperature goes up, then your energy goes up and your speed goes up. You just have to choose the one that works best for your scenario. I would choose the one that is the easiest. Okay, so for number 8, we want to find the ratio of the gas after it absorbs the heat, right? V2 over V1. So if I just look at the temperature, right, it starts at 332, and then it goes up to 1,660. If temperature goes up, the energy goes up and speed goes up. So that means my second speed should be bigger than my first speed. So that means I should get a number that's bigger than 1. So based off that, I can automatically eliminate 2 answer choices, right? The ones that are smaller than 1 or equal to 1, you can eliminate because you know your velocity goes up. But we want to be more specific on like how much it goes up. So we have to like do a little more math. So for this one, we're only giving temperature. So you can either use like this one or this one. But since we want the average speed of the gas molecules, so like V bar is average speed. So I want to use the one in the middle because that one has like V in it. And so like, or use that one because like this one doesn't have speed in it. If you really want to, you could use that one, but we don't have pressure. We don't have volume either. So like that one's a little harder. And also we don't have temperature. Or we do have temperature, but it's not the equation. So using the middle one would be the easiest. Okay, so I'll just do 1/2 mv squared is equal to 3/2 Boltzmann's constant times temperature. Yeah, so if we know the temperature, which they gave it to us, we know Boltzmann's constant, it's a number. We can use that to solve for like the velocity. So since we're solving for like a ratio, we'll get like put like V2 and T2 and 1/2 mv1 and T1. So if we got V2 over V1, you could solve for your velocities like individually. So like you multiply everything by 2, right? And then divide by m and solve for the velocity. And it doesn't really matter what number you put for m because it's like the same. So you can put 1 for m, 1 for kb, and you solve for velocities, and you'll get like a number for velocity, and then you get a ratio. Or you can just like divide your equations, right? So you get V2 over V1. So if I divide our equations, right, the 1/2s cancel out, the m's cancel out, the 3/2s cancel out, the kb's cancel out. So what you really get is like V2 squared over V1 squared is equal to T2 over T1. And then we just want V2 over V1, right? Not squared. So you just take the square root, and then that's how you can like get your answer. But whatever way makes sense to you is the one you should use. So if you are not comfortable with dividing 2 equations, you can just solve for velocity individually and then get your ratio and then get that as your answer. But if you are comfortable with like the algebra dividing equations, then you can just divide your equations and get the ratio and then just plug the numbers. Okay. So the next few ones are like what you could see on your test using like these equations that like I briefly talked about. And you just have to choose the one that's best for you. So like for number 9, right, they want internal energy. So internal energy is U. So we'll just use the one with U in it. So that's that one. And you see if you have everything and solve in one step. And if you do, great. And if you don't, then find it and just do it. And then the next one, number 10, is total translational kinetic energy. Again, like total kinetic energy, that's like internal energy, because internal energy is like all the energies of your gas. So again, you'll use the same thing, right? You'll use U is 3/2 nRT, right? U is like total energy, so that's what we want. But then like the problem becomes that like, well, we don't have T, we don't have R, and we don't even have, or I guess we do have R, but we don't have N. But it's, you can always assume it's an ideal gas because like, that's what this class is. So the ideal gas law, PV equals nRT. So instead of using nRT, right, since PV equals nRT, right, we can substitute the whole thing nRT with PV. So U is equal to 3/2 pressure volume. And then you can just plug that in, and then you can solve for U. The only thing you have to be careful about, again, we want our pressure in pascals, so turn that ATM to pascals. We want our, I guess the temperature is in the equation, but we want our liters to be in cubic meters, so you convert to cubic meters. And the conversions on your formula chart, they're also in the previous question, right? They're right here. So make sure you convert to cubic meters and pascals. And you'll be given the conversions, so you don't have to memorize them. Okay, so for number 11, we're looking for the average kinetic energy of a gas molecule. So if you're looking for like the average kinetic energy, it's gonna be like this one right here. So then you just do it. Again, we're not given temperature, right? So you have to use the ideal gas law to find temperature. All right, trust you all can do that. Just make sure that, again, ATM you convert to pascals, and liters you convert to cubic meters. So you'll find temperature using the ideal gas law, and then you can use that temperature, put it into our equation, and then you will solve for average kinetic energy. Okay, so then the last one, like you should be able to do this one. So this one says like you have a spike hammered to a railroad, right? Railroad tie, whatever that means. I guess it's like you are working on the Trans-Pacific Railroad. Like there's a little railroad, there's a nail, you have your hammer, and then you like hammer the nail, I guess. And it absorbs some percent of the kinetic energy as internal energy. If you forgot the formula for kinetic energy, it's 1/2 mass times velocity squared. So you figure out what percentage of that kinetic energy goes into internal energy, and then like that's your answer. Because if like I have, I don't know, if I am, I guess there's a better analogy. If I have like $100, right? So you have some amount of kinetic energy, and you transfer 50% of it to someone else. So if I'm transferring 50% of my $100 to my brother, then my brother gets 50% of $100. So the hammer is me, then the spike is my brother. So then the hammer is giving 40.3% of its energy to the spike. So then you figure out what 40.3% of the original kinetic energy is, and that's your answer. I trust that y'all can do that. That's logic. Well, I'm very excited to go to the zoo tomorrow. I hope you have enough information to finish your homework. The due date is on the calendar. So good luck.